In this video, I want to look at three basic geometric properties of the definite integral. To get started, I want to consider the integral from a to a of f of x dx. And I want to actually draw a picture of what's going on here. So here's my xy coordinate axis, and here's the function y is equal to f of x. Now, the fact that our upper and lower endpoints are both a basically means that I'm looking at the area of a line segment. In other words, I'm really looking at the area trapped underneath y is equal to f of x and over the line segment a to a. So this particular integral is nothing more than the area of a line segment. But areas of line segments are known to be zero, and consequently we can say that the definite integral from a to a of f of x dx is always going to be equal to zero because it's just the area of a line segment. The next particular property is one that allows us to break an integral up. So I'm going to actually draw a region. And here is my function y is equal to f of x. And we'll make a here, and we'll make b over here. And this particular piece of area that I've shaded in white is the area of it's given by the integral from a to b of f of x dx. That's equal to what I'm going to call the white area. Now I want to let c be any number that is between a and b. Now what that means is that I have a line here that corresponds to x is equal to c. And this line subdivides the white area into two regions. One that I'm going to shade in this kind of an orange color. That orange area is the integral between a and c of f of x dx. And let's use this color here. This kind of blue-green color, I'm going to call it a green. Well, actually, let's call it a blue. That blue area is equal to the integral between c and b of f of x dx. And it is quite clear that the white area is equal to the orange area plus the blue area. That's clear just from looking at the picture. And this has important consequences. The white area, remember, is the integral between a and b of f of x dx. And that is going to be equal to the orange area, which is the integral between a and c of f of x dx, plus that blue area, which is the integral between c and b of f of x dx. In other words, we can split an integral up anytime we want to, at any point that's between the two endpoints. So I kind of want to state that as a formal fact. So our fact is going to be that if I have an intermediate value between a and b, then I can split the integral between a and b of f of x dx up at that intermediate value and get that the integral from a to b of f of x dx is going to be the sum of the integral from a to c of f of x dx plus the integral between c and b of f of x dx. Now our third basic property is one that is based on the fact that continuous functions have a very nice property. So I want to remind you of something called the extreme value theorem. from Calculus 1. And the extreme value theorem says that if I have a function that is continuous on a closed interval, so I'm going to let f of x be continuous on the closed interval between a and b, then I know that f attains both a maximum value and a minimum value on that closed interval. And what this means in terms of a picture is this kind of a thing. Here's, of course, my x-axis and my y-axis, and the function can go up and then it might go down, but somewhere it's going to have a maximum and a minimum value. And let's say that that's A and this is B over here. And in this particular picture, the maximum value up here is at this particular point. So y equals capital M is my maximum value. And in this particular picture, the minimum value would be over here. Y is equal to little m, which is the minimum value on this particular integral. And I want to kind of look at this particular picture and draw some rectangles. So my first rectangle, I'm going to use that minimum value, and I'm going to draw a rectangle for the whole interval. Now that orangish rectangle has area equal to little m times b minus a. And let's get another color. Let's use this color here. If I look at this green, and I draw this green rectangle that has height equal to the maximum value of the function, so there's the height of this green rectangle. The green rectangle has area capital M times b minus a. Now, I want to also shade in a white area. This white area is, of course, the integral between a and b of f of x dx. And if I look at the picture, it's quite clear that we have an important fact. The white area is going to be bigger than the orange rectangle, and the white area is going to be smaller than the green rectangle. And this is another important fact about bounding integrals. And so I want to put that, I want to list this fact as an important fact to remember as well. So we're going to have this fact. If f is continuous on a closed interval between a and b, and f of x is always trapped between capital M and little m on my closed interval between a and b, then it turns out that the definite integral between a and b of f of x dx will be less than or equal to capital M times b minus a, and it will be bigger than or equal to little m times b minus a. And those are the three facts that we're going to look at in this particular video.